Hello all, welcome to today's lecture. In today's class, we'll be talking about the column splices and its design procedure in compression members. So, what actually a column splice and when column splices are required and what are the different types of column splices? Let's look into these terms. So, what is this column splice and when it is provided? Column splice is nothing but suppose when you have a section. Okay, so consider this as the two-story building. Okay, this is the ground floor and this is the first floor. Okay, now when you are constructing the structures, okay, say for example you have another story which is also second floor. Okay, so when you have this kind of steel structures which is of having a height more than g plus 2 g plus 1 kind of structures, and here obviously we need to use the steel members only as a column section and as well as the beam section. So forget about beams for time being. Let's look at column sections. You don't find, suppose say for example, each floor height is 4 meters. Okay, each floor height is having 4 meters. Now, when you go into the workshop or when you go to the industry where the steel sections are being manufactured, you might not find the exact 4 meters height of the column sections. Suppose say for example, you are using I sections here as the column members or the angle sections or L-shaped sections. So when you go to the industry or when you go to the shop and ask, you need 4 meters height of an I section, you might not find exact 4 meters, right? You might find, say for example, you find the largest maximum length of 3 meters span. But you have to construct a structure which is of height 12 meters, you can say. Just this is an example. So your aim is to construct a structure which is having 12 meters height, but the available length of each section is only 3 meters. Now what will you do? So you have to provide 3 meters at one section, and again the next 3 meters has to be provided, and similarly likewise you are going to provide the 3 meter spans. Now in concrete structure, what you are going to do is you are going to pour the concrete and then you are going to construct the structure with the reinforcement, with the help of reinforcement which is available. But here you don't have any amount of concrete. Okay, so we have only the steel sections. Now how will you join? So if you want to join two sections or two steel sections, you have to provide a part which is called as splicing. And when the splicing is done for the column sections, it is called as a column splicing. That means joining of two members. Remember, the column splice can be defined as a joining of two members in order to produce the required height or the required length for the structure. That's what the column splice is. Okay, so when you have the insufficient length or height of the member, in order to produce the sufficient height and sufficient length of the member, then you are going to require the column splicing. So let's look at the figure which talks about the column splicing. See, you have the first section which is of first I section, and you also have the second I section, and these two sections, that is the I section 1 and I section 2, are jointed by using plates. Okay, this plate which is called as a splice plate. Okay, so these plates are called as splice plates, and splice plates are provided. So this splice plate are provided on either sides of the column flanges. Okay, so you have the splice plate along this end and you also have the splice plate along this end. You can only see the bolts on the other side, right? So technically the splice plates are provided on either sides of the flanges of the I section. So these are the flanges. This is the one flange and this is also the another flange. So on either side, wherever you are joining the two members, this portion is the joining portion. So by joining these two members, you are going to provide the splice plate. In simple terms, they are a double cover butt joint. Okay, in order to remember in a simplest way, they are the double cover butt joints. So you have the section 1 on one side and section 2 on the other side, and then you are going to provide the splice plates, and hence the connection is called as the column splicing. And here one more thing which you have to remember is, depending upon the requirement, you are also going to provide the splice plate onto the web of the I section. This portion is the web. Okay, so this entire portion is the web. So onto the web of the section, you are also going to provide the splice connection. So when you provide the splice connection on the web, it is called as web splicing. Okay, when you are providing the splicing along the web, it is called as web splicing. And when you are providing the splicing along the column, along the flange of the column, then they are called as a flange splicing. Okay, so in the design conditions, you are going to design both the web splicing as well as the column splicing. Now let's look at what are the different types of splicings we have based on the load. So we have three different types of column splices. The first one is splices for axial load. That means you are going to design the splices only when there is an axial load, and splices for moment, and the last one is splices for the shear. So these are the three cases. In some cases, you might experience only the moment and load. In some cases, you might experience all the three, or in some cases, you might experience any one of the three. So it depends on the situations. So however, we are going to design for all the three cases in the design of splices. Let's look into this diagram in a very detailed way. So this diagram talks about very clearly about the flange splicing and the web splicing. So the plate which is there, okay, this plate is called as a flange splicing. See, you have an I section, okay, and along the web, along the flange of the both I sections, here you have the first I section and this is the second I section. You can see a clear-cut difference here. Okay, the thin line. So you are joining two I sections by using the plate which is called as a splice plate. When you are providing splice plate to the flanges, then they are called as flange splicing. And when you are providing splices along the web, then they are called as a web splicing. So that means here you are going to design two types of splicings. One is the flange splicing and the second one is the web splicing. For both the things, you are going to find out the number of bolts and then the arrangement has to be done. So the second figure talks about the simplest arrangement which can be made. Okay, so let's solve a problem and understand how to design the column splicing. So here you can see the problem which is based on splicing of compression member. So here it is not tension, it is compression. So the heading you can keep it as splicing of compression members. Anyways, so here what we are going to do is we have a section which is ISHP 300 at the rate 618 Newton per meter column, which has to be spliced at a section, and it is subjected to an axial factored load of 500 kilonewtons and factored moment of 30 kilonewtons meter and factored shear force of 100 kilonewtons. And you have to design a column splice and ends are machined. So this is one thing which you have to focus on. So ends are machined to provide the full bearing. Now here in the problem, if you clearly check down, the three parameters are given. The first one is the load. Okay, so we were talking about the types of column splices. So one is based on the axial load. Okay, and the second one is based on the bending moment or moment. The third one is based on the shear force. So in this problem, you have to design for all these three cases. That means the column that is ISHP 300 is experiencing all these three forces. Let's look at how to solve this kind of problem when the shear force, the axial load, and bending moments are given in the question. So the solution goes in this way. So initially, let's write the given data, which is provided for us. So given, so the axial load or the factored axial load, factored axial load equals to 500 kilonewtons, and factored moment or factored bending moment, anything the same. Factored moment equals to 30 kilonewton meter. And the last one is the factored shear force, which is 100 kilonewtons. Okay. Now we are also given with the section that is ISHB 300. So let's write the sectional properties of ISHB 300. Okay. So let's write it this way. The sectional properties of ISHB 300 at the rate 618 Newton per meter are, so the first one, let's write the height of the section, that is 300 mm, and the width of the flange, that is BF, which is equals to 250 mm. And the next one is the thickness of the flange, which is 10.6 mm. So let's keep these values for time being, and any other required values we can make it at the time of requirements. Okay, so these are the sectional properties of ISHB 300 at the rate 680 Newton per meter. So these values are obtained from steel tables book. Okay, so these values are obtained from steel tables book. Now let's solve the first step, that is the load transfer on each flange. So let's write the first one. The first step you can make it as load transfer on each flange. Okay, so load transfer on each flange. So what is this load transfer on each flange? So for one I section, you have two flanges. Okay, for one I section, you have two flanges. So therefore, so load transfer on each flange. Let's write one more time here. Load transfer on each flange equals to, what is the load that is getting transferred? It is 500 kilonewtons. So 500 kilonewtons upon 2. Why 2? Because we have two flanges for the I section. One is the top flange and the other one is the bottom flange. So this is the top flange and this is the bottom flange. So 500 divided by 2 will give you 250 kilonewtons. Okay, this is the amount of load transferred on each flange. Now, as I was telling, for both the flanges, you are going to provide the column splice or splice plate. That means you have to provide two splice plates, one on the top and other on the bottom. So the next case is load transfer on one splice plate. One splice plate. So you have two splice plates. Okay. So in this, that is in 250 kilonewtons, you have the load will get distributed to each splice plate is, or you can make here it as one each splice plate. Each or one, they both are same, which will be 125 kilonewtons. So this is the amount of load which is getting transferred on each splice plate. Okay. Now let us assume, okay, let us assume 6 mm thick as the splice plate. Assume 6 mm thick of splice plate. So initially we don't know the thickness of the splice plate. So let's assume and let's check whether the assumption is correct or not based on the various categories. So let us assume 6 mm thick of the splice plate and load transmit to one splicing plate due to moment. Okay, so load transmitted to one splice plate due to bending moment. So what should be the load that is getting transferred due to the action of bending moment? So how will you find this? So this can be found out in this way, that is bending moment, that is capital M, divided by h of the I section, that is height of the I section, plus the thickness of splice plate. SP represents splice plate. So the thickness of the splice plate. So this will be, the moment is given in the question, which is as 30 kilonewtons meter. So 30 into 10 power 6, which will be in Newton mm. Okay. So divided by height of the I section is 300 mm. So here you can see height of the I section is 300 mm plus the thickness of the splice plate. So we have assumed the thickness of the splice plate as 6 mm. So therefore, this value can be obtained as 98.03 kilonewtons. So this is the amount of load that is getting transferred on one splicing plate due to the action of bending moment. So therefore, the total load on one splice plate. Therefore, the total load on one splice plate. Okay, so the total load on one splice plate is actually the addition of load transferred on each plate and load transferred due to bending moment. Okay, so the total load on each splice plate or one splice plate equals to load transfer on each splice plate and load transfer on each splice plate due to bending moment. That is 125 plus 98.03. So which will be 223.03 kilonewtons. So this is the amount of load which is coming onto each splice plate. 223 kilonewtons is the amount of load. Now let's find out the area of the splice plate, and by using area, let's find out the values of width and thickness of the splice plate. So sectional area required for one splice plate. So we are all calculating for only one splice plate. So if you know the one splice plate dimensions, then obviously the same replicate can be done for the other splice plate as well. Okay. So sectional area required for one splice plate. So this can be calculated as the total load on each splice plate, that is 223.03 kilonewtons, which I'm converting into newtons. Okay, divided by Fy, that is 250. So the formula can be written as P by Fy. This is the formula. P value is the total load on each splice plate, and Fy value is 250 megapascals. And this will be 892.12 mm square. So this is the area of each splice plate. And by using this area, let's find out the width and thickness of the splice plate. Okay, so the width of a splice plate is actually taken as width of splice plate is actually taken as the width of flange of column. Okay, So the width of splice plate is taken as width of flange of column. So what is the width of flange of column? It is 250 mm. So therefore, the splice plate width is also 250 mm. So remember, the width of splice plate is actually taken as width of flange of the column section, that is BF value. So therefore, BF width of the splice plate is equals to 250 mm. Now let's find out the thickness of the splice plate. Thickness of splice plate. Okay, so the thickness can be calculated as, we know area equals to length into width or length into thickness. So we know the area value, which is 892.12, and we also know the length or width, which is 250 into T. So if you solve this one, then you will get to know the thickness value. Okay, so let's look at this. So the thickness of splice plate required equals to area, that is 892.12, divided by width, that is 250. So which will be 3.56 mm. But what is the area, what is the thickness of the splice plate which we assumed? It is 6 mm. Okay, so let us provide the 6 mm thickness of splice plate only, because what we have got, so we have assumed 6 mm thickness of splice plate. Okay, we have assumed 6 mm thickness of splice plate, but how much we can provide is 4 mm or 3.56 mm. So let's keep the same assumption, which is 6 mm. So therefore, the thickness of splice plate equals to, therefore, the thickness of splice plate equals to 6 mm. Okay, so now we have got the width and the thickness of the splice plate. So let's find out, let's design the connections. So the second step can be taken as the design of connections. Design of connections. What is this? So here we are going to design the connections for flange splice plate. Okay, you can keep this heading as design of connections for flange splice plate. We have already talked that the splice plates are provided for both the flange as well as web. So whatever we have done so far, it is all for flange only. Okay, so let's design the connections for flange splice plate. So how will you design? So here we are assuming M20 bolts of grade 4.6. It is just an assumption. So in order to find out the number of bolts, so design of connection is nothing but to find out the number of bolts, that is n value. So the n value can be found out, that is number of bolts can be found out by the factored load upon bolt value. Factored load upon bolt value. So let's find out this bolt value. So bolt value is actually the least of strength in shear, that is VDSP, and strength in bearing, that is VDPB. Okay, let's find out these values. So the first thing is strength in shear. So the strength in shear is denoted with VDSB equals to VNSB by gamma MB, where VNSB equals to FUB by root 3 NN ANB plus NS ASB into 1 by gamma MB. Now here assume NN equals to 1 and NS equals to 0. Okay, so while designing the splicing in the compression members, assume NN equals to 1 and NS equals to 0. Let's solve for this. So the value of FUB is 400 because we have assumed the grade of bolt to be 4.6. So FUB by root 3, NN value is 1, and ANB equals to 0.78 pi by 4 into D square. So ANB formula is 0.78 pi by 4 into D square, where D is the diameter of bolt. So we have said that we are going to use M20 bolts, that means 20 mm diameter bolt, plus NS value is 0. So again, anything into 0 is 0, however, into 1 by gamma MB, which is 1.25. So here you will get the gamma VDSB value as 45.2 kilonewtons. This is VDSB. Now we also have to find out the strength in bearing. Strength in bearing. So the strength in bearing is calculated using VDPB equals to VNPB by gamma MB, where VNPB equals to 2.5 KB DT into FU. So this is the formula of VNPB divided by gamma MB. Now, in order to find out the value of KB, you need to know the edge distance and the pitch distance. So edge distance can be calculated as 1.5 into D naught, and pitch distance is 2.5 into D naught. Sorry, 2.5 into D. So the minimum edge distance equals to 1.5 into 22, where D naught is diameter of bolt hole, which will be 1.5 into 22. So that will be, you will get it as 33 mm. So I'm considering it as 40 mm. And 2.5 into D, where D is the diameter of bolt, which is 20 mm. So this will be 50 mm. Okay. So from this, you know the KB is the least of E by 3D naught, P by 3D naught minus 0.25, FUB by FU, and 1. So among all these four, the least value has to be adopted. Okay. So after finding out the least values, the KB value is obtained as 0.5. So if you substitute the values in the above four formulas, you will get to the least value of KB as 0.5. So therefore, I'm directly substituting, which is 2.5 into KB into D. D is the diameter of bolt, which is 20. And here, T is the thickness of the splice plate. So the thickness of the splice plate is 6 mm. So the thickness of the splice plate is 6 mm. You can make it here. It is the thickness of splice plate, SP. Okay. So now into FU is 410 into 1 by 1.25. Okay. Now, when you solve for this one, you're going to get the answer as 48 kilonewtons. So this is VDPB. Therefore, bolt value equals to, so what is the bolt value? It is the least of VDSB and VDPB. Okay, so the least value is 45.2 kilonewtons. So bolt value is the least of strength in shear, that is VDSB, and strength in bearing, that is VDPB. So therefore, number of bolts required. Therefore, number of bolts required. N equals to, I told you already, N equals to factored load by bolt value. What is this factored load? It is the total load on each splice plate, that is this one. Okay, that is 223.03 kilonewtons. So the factored load is 223.03 kilonewtons. So 223.03 divided by bolt value, which is 45.2. So approximately you will get 4.92 bolts So I'm making this as 6 bowls. Therefore, provide 6 bowls for the flange splice plate. Therefore, provide 6 bowls of 20 diameter for flange splice plate. So this design is for the flange splice plate. Now let's solve for the web splice plate also. So before doing that, let's write down the splice plate dimensions or flange splice plate dimensions are, okay. So we have got 360 and 250, which is the width, and the thickness is 6 mm. So this is the values of the length, width, and the thickness of the splice plate. Okay. This is actually limited to flange splice plate. Okay. So here the 360, that is the length of splice plate. I have to find out. Let's find out the length of splice plate and then let's write this statement. Okay. So the length of splice plate or flange splice plate, because we are providing it for flange only. So length of flange splice plate equals to, how is it calculated? It is calculated as 2 times of edge distance plus 2 times of pitch distance. 2 times of edge distance plus 2 times of pitch distance multiplied by 2, whole multiplied by 2. Okay. So the 2 times of edge distance is 40 mm and 2 times of pitch distance is 50 mm and whole multiplied by 2. It will be 80 plus 100 into 2, which will be 360 mm. So that's how this value has come from. Okay. So therefore, the length of the splice plate equals to 360 mm and the width of the splice plate is actually the width of flange of the I section, right? That is what we have assumed here. So width of splice plate, that is B equals to 250 mm and the thickness T equals to 6 mm. That's how I got it here, right? Now, whatever we have designed it for the flange splice plate. Let's design it for the web splice plate. So the third step is design of web splice plate. Design of web splice plate. So technically, the web actually resists the shear force. So if you take the I section, the function of the web is to resist the shear force. So here we are going to consider only the shear force values. Okay. So let's write this in the statement form. The splice plates or the web splice plates, the web splice plates are provided on either sides of web of column. I was telling you, you are going to provide the splice plate on either sides of the web of column. On either sides of web of column. Okay, so why we are providing it is to resist shear or to resist shear force. Okay, so let's write down the factored shear force which is given in the question. The factored shear force which is given in the question is, it is 100 kilonewtons. Okay, that is given in the question. So the factored shear force is 100 kilonewtons. Okay, and how many web splice plates you are providing? You are providing 2 web splice plates, that is one here and the other one here. So each one has to carry half of the load. So therefore, shear on each splice plate equals to how many we are providing? 2. So that's the reason why I'm dividing it 2. Therefore, it will be 50 kilonewtons is the amount of load which will be coming onto the each web splice plate. Okay. Now let's find out height of web between flanges. So height of web between flanges. Between flanges. What is this? So it is actually this one. The height of the web between the top flange and bottom flange. This one you are going to find it. So how will you find out this one? So we have a fixed formula for this. That is, let's consider as the total height of the I section. Okay, the total height of the I section minus 2 times of thickness of flange. The total height of the I section minus 2 times of thickness of flange. What is the total height of the I section? It is 300 mm minus 2 times of thickness of flange. The thickness of the flange is 10.6 mm. Okay, so here you can see that one. The thickness of the flange is 10.6 mm. So that will be 300 minus 2 times of 10.6 will give you 278.8 mm. So this is the height of web between the flanges. Now, how much width of the splice plate has to be provided? So width of splice plate, width of splice plate. So actually, what is this value representing? That is 278.8 mm represents you. If you want to provide the web splice plates, it must be in this length only, because the splice plates for web are connected to web only. So whatever is the height of the web, in that height only you have to accommodate the splice plates as well. Okay, so now the width of splice plate equals to total height of the I section divided by 2. It is half of the height of the I section, which will be 300 divided by 2, which will be 150 mm. So the height, the width of the splice plate equals to 150 mm. Now, let's find out the design shear stress, and from this, let's get it the value of thickness of the splice plate. Okay, so let us consider, let T be the thickness of web splice plate. T be the thickness of web splice plate. Now, in order to find out the thickness of the web splice plate, let's have to focus on the shear stress or the shear force. So the design shear stress, design shear stress equals to, we have a formula that is Fy by √3 into gamma m naught, where Fy is 250 and √3 into gamma m naught is 1.1. So the design shear stress is 131.2 newtons per mm square. Okay, now this value has to be equated to the maximum shear stress. So let's find out the maximum shear stress. So what is this maximum shear stress? It is tau max. Okay, so if you go back to the concepts of strength of materials 1, so the maximum shear stress is taken as 3/4 of, 3/2 of average shear stress, that is tau average. 3/2 of tau average. Okay, so from this, let's equate these two values and let's find out this. So consider this as equation 1 and this as equation 2. So if you equate 1 and 2, it will be, so the first equation is 131.2 equals to 3 by 2 of average shear stress. So how will you find out the average shear stress? It can be find out as shear on each splice plate, shear on each splice plate divided by width of splice plate, into the thickness of splice plate. Okay, what is the shear on each splice plate? It is 50 kilonewtons. You can see here, shear on each splice plate is 50 kilonewtons. So let's solve for this. That is 131.2 equals to 3 by 2 of the shear on each splice plate is 50 kilonewtons. I'm converting into newtons, where width of the splice plate is 150. Okay, the width of the splice plate here we have got that. So 150 mm into the thickness. So if you solve for this, the thickness is obtained as 3.81 mm, which you can take approximately as 6 mm, or you can also take 4 mm. So therefore, provide 6 mm thick web splice plate. So therefore, provide 6 mm thick web splice plate. So now you have designed the web splice plate also. Now you have to connect this web splice plate. So the next step can be, the fourth step can be design of connection. Design of connection. So you have to connect the flange of the you have to connect the web splice plate to the web of the column. How will you do this? So here also you have to find out the number of bolts. So number of bolts equals to factored load by bolt value, where bolt value can be found out by VDSP and VNSP values least, that is strength in shear and strength in bearing. So let's find out the strength in shear. Strength in shear. So here actually you are going to experience the double shear values. So the strength in shear, actually you are experiencing the double shear values. So therefore, VDSP equals to 2 into, sorry, VDSP equals to VNSP by gamma MB. Here also again, NN equals to 1 and NS equals to 0. Consider it this way. So this, if you substitute into 2, because it's a double shear. So if you solve for this one, then you're going to get the answer as 90.5 kilonewtons. Okay, same as the previous step. If you solve, so you will be getting it as 90.5 kilonewtons. So let's solve for the strength in bearing as well, which is strength in bearing. So this is calculated using VDPB, same as we solved in the previous two steps. So which is VDPB equals to the VNPB by gamma. So you can solve for this one. Okay, and out of this, after calculating VDPB value, the bolt value will be the least of VDSP and VDPB. So it is actually the least of VDSP and VDPB. So VDSP value you're going to get as 90.5 and VDPB you're going to get it as 48 kilonewtons. So just solve for the same values. Assume edge distance and pitch distances as we have assumed in the third step on. Okay. So now, therefore, the bolt value equals to 48 kilonewtons. So it is the least of strength in shear and strength in bearing. That is this one and this one. So the least is obviously 48 kilonewtons. Therefore, number of bolts required. N equals to factored load by bolt value. Now here factored load is the load which is coming onto each splice plate. So what is the load that is coming on each splice plate? It is 50 kilonewtons. So therefore 50, that is factored load, by bolt value, which is 48. So this will be 1.04 bolts. You can take it as 2 bolts. Therefore, provide 2 bolts of 20 mm diameter for web splice plate. So that's how the connection is designed. So that connection diagram will look in this way. Please have a focus on the connection diagram. So this is the connection details. So here actually there is a small correction. So the edge distance is not 30 here, it is 40 on all the sides. Okay, here also it is 40 mm. Okay, and this is how the web splice plate and the column splice plate or a flange splice plate has to be connected. Okay, so you have 6 poles, you have got 6 poles for the flange splice plate. So 6 poles on one side and the 6 poles on the other side. Similarly, you have got 2 poles for the web splice plate. So you have the 2 poles on the top and 2 poles at the bottom for the web splice plate. Similarly, 6 poles for the column or flange splice plate. So this is the first figure shows the elevation, that is from the front view, and this shows from the side elevation. When the same thing has to be seen from the side, you will be seeing only these 6 poles. This one. Okay, from any one of the sides, you are going to see the 6 poles. So you cannot see these 4 poles which are there for the flange splice plate. However, this is the connection details. So in the next class, we'll talk about the other topic. Thank you.